Now let's look at our second example, how to sketch a phase diagram for a two-dimensional dynamical system. We start with looking at what kind of knock lines we have. So we have x prime is equal to f of xy, and the function is negative x plus xy minus x squared. And we set to 0. And if we look at this equation over here, we see we have a common factor x we can factor out. That's negative 1 plus y and minus x is equal to 0. So really, if we set f of x, y equal to 0, we have two knock lines. One is x equal to 0, the other one is negative 1 plus y minus x is equal to 0. Or you can say y is equal to x plus 1. And these are called x knock lines because along these lines x prime of t is equal to 0. And let's look at the second one. These are called y knock lines. And we have y minus xy is equal to 0. We factor y out. Again, we see we have two knock lines. One is y equal to 0, and the other one is x is equal to 1, or 1 minus x equal to 0. Now let's draw these lines in the xy plane. So this is what we're going to have. This is y, and this is x. Okay. Let's use different color for different knock lines. For the x knock line, we're going to use red. So this is the one we have. This is y is equal to x plus 1. And we have another one. And the other one is x is equal to 0. So that means we have over here, this is the one. This is x equal to 0. So we have two. X is equal to 0, and this is y is equal to x plus 1. Again, we can put short line segments over here. Along these x knock lines, x direction derivative 0, so we only have vertical velocity. Y prime isn't 0. So we put these things over there. Okay. Now let's draw the y knock lines. We also have two. Y is equal to 0. That's x-axis. We're going to use green. And then we have another one. Is x is equal to 1. This is x is equal to 1. So we have two. And along these two lines, we have horizontal line segments because y prime is 0. Now we're going to determine the directions or the signs of the derivatives. Let's look at the red one first. For the red one, we look at y because x is already 0. So that means we are looking at this expression over here. Now if x is bigger than 1, 1 minus x is negative. So when y is positive, then this is negative. So here we have going downward, arrows going downward. And once you pass this one, then 1 minus x becomes positive and y is still positive. And you will go all the way until when y becomes negative, then it changes direction again. On this line, x is 0, so 1 minus 0 is 1, and y over here is positive, so this is the one we have. And then when y is negative, it goes down. So we finished the red lines. Now we do the green lines. When the green lines, we look at x. So on this y equal to 0 on the x-axis, we have x times 1 minus x times negative 1 minus x. So if x is positive, then we have the sign negative. So here it's always going to be negative. Until x changes sign, and then it becomes positive. If x is over here, then it's going to be positive. Then when x crosses negative 1, it changes sign again. This is the one. And then let's do the vertical line, x equal to 1. If x is equal to 1, let's write it down. Over here, x is equal to 1, so we are looking at the sign of x, negative 1 plus y minus 1. So really it's x, y minus 2. And that would be our x derivative of t on this line. And then x is also 1, so really you're looking at y minus 2. Look at y minus 2. If y is bigger than 2, that's over here, it becomes positive. If y is less than 2, it's negative. If we have all this information accurately drawn in the plane, then we can decide the dynamics. So if you have an initial value over here, then the dynamics is going to drive this point down and left, go this way. If it's over here, right and down. If it's over here, up and right, and it's over here, left up. Okay. And if you look at what's going to happen over here, whenever you see the intersection of green and red lines, you have an equilibrium. So you can see this is an equilibrium, and here is another one, the origin, and here you have another one. And we can determine the stability by drawing arrows around it. So if you have initial value over here, it's going to go cross over here, and then it's going to go up, and then it's going to go left, and then it's going to come down and it's spiral in. So this one over here is stable. This one over here is a stable spiral. The origin is unstable, and it's a saddle. And this point over here, I think, is unstable as well. You can easily see this one over here is unstable. And of course, all these properties of the equilibria can be confirmed if we actually use the derivative test. And that will be in another segment.